Today we will discuss the topic, and this is nuclear binding energy. Okay, so nuclear binding energy is basically refers to the missing energy to the missing energy which is which is responsible to keep the nucleons bind altogether in a nucleus. So this is basically nuclear binding energy basically refers to the missing energy. This is important terminology which has to be understood when we try to understand the nuclear binding energy concept. So uh, before going to what is missing binding energy, let us do one small exercise that which is that what is the energy equivalent of one atomic mass unit. So what is the energy equivalent of one atomic mass unit? So in my last lecture, I had discussed about what is one atomic mass unit. So how to convert atomic one atomic mass unit? Uh, we will use the famous equation E equal to mc square. E equal to mc square, and where m is in will be in atomic mass unit. So this, if you write E equal to mc square, so because we know that one atomic mass unit is equal to 1.66054 into 10 to the power minus 27 kilogram. So then I'll write this mass is 1.66054 into 10 to the power minus 27 kilogram, and then we have 3 into 10 to the power 8 meter per second c square. So this will give you this will give us that 14.944 into 10 to the power minus 11, and then kilogram meter square second minus 2. And you know this is equivalent to joule. So this is equivalent to, so this is 14 point, I can write it 944 into 10 to the power minus 11 joules. Okay, so now we want this a joule to convert in electron volt. Now I want this joule to convert in electron volt unit. So this is electron volt unit. So because we know that one electron volt is 1.6 into 10 to the power minus 19 joule. So what I have to do is I'll divide this number. I will divide this number by 1.6 into 10 to the power minus 19 joule to get this energy into electron volt. Okay, so this E, if I divide E, if we want E in electron volt, this will be 14.944 into 10 to the power minus 14 joules, and I'll divide this by 1.6 into 10 to the power minus 19 joules. So per electron volt, so this will give us, this is around 931.49 into, or this will be like 9.31. Let me correct it like this. So this will be around uh, 19.4. So this, okay, so this will be 931.49 into 10 to the power 6 electron volts, or this we can write as 931.49. 10 to the power 6 correspond to the median electron volt. So finally, you can write that that's one atomic mass unit in terms of energy is 931.49 MeV in terms of energy, in terms of energy equivalent. Okay, so this is important, you must remember, because when we discuss the binding energy, so then to calculate, we'll talking about uh, the everything in terms of the energy, so we must know that how much atomic mass unit or atomic mass is equivalent to the energy unit. Now let us come to the nuclear binding energy. So what nuclear binding energy is, that as I already defined, that it refers to uh, it refers to the missing energy which is responsible to keep the nucleons bind all together in a nucleus. So to understand this, let us take one example. So we will try to understand this through one example, and then we'll consider the deuterium isotope. So isotope of hydrogen is deuterium, which is, we know that this is 2 hydrogen 1. This is an isotope of hydrogen. And what is hydrogen? This is 1H1. So in deuterium, this is what we have, is we have one proton and one neutron. So this is made up of, I can say this, and this you can I say this hydrogen is one proton only. There is no neutron. Okay, one proton only. So this I represent hydrogen as this is my hydrogen, in which I have one proton, in which I have one proton, and the electron is there. This is my proton. So this is my electron. So this is my hydrogen atom. This is my 1H1, and then the mass of this hydrogen atom is, I will write, is 1.007825 atomic mass unit. Okay, MHU. And if I add one neutron to this system, this is my, say this is my neutron, this is my neutron, this is neutron, and the mass of the neutron is 1.008665 U. So what I'm going to do is, if I take this neutron and add it to the hydrogen system, then what I'm going to have, a system which is in which I have one proton and one neutron sitting inside, okay, in the nucleus, and then one electron is there. So this is my isotope of hydrogen, that is deuterium. this one. Okay, and the mass of the deuterium, say like deuterium experimentally is deuterium, this is deuterium atom, this is hydrogen atom. So mass of the deuterium atom is found to be 2.01410 atomic mass unit. This is experimentally verified. Ex this mass is experimental mass. Okay, so this is the actual mass which this deuterium atom is having. Now let us add the mass of these two, because ultimately this deuterium atom is being made by supplying one neutron to this atom. So if I add the mass of this hydrogen atom and the mass of the neutron, then this will be equal, this must be equal to the mass of the deuterium atom. So if I add the mass of the hydrogen atom and this uh, neutron, so let me do this. If I add it like this, if I add the mass of the hydrogen atom, so this is 1.007825 atomic mass unit, and if I add plus the mass of the neutron, so this is, I'm going to add 1.00, this is 8665 U. If I add these two, what I'm going to get, so this is what I'm going to get, so this is expected mass of the deuteron. Okay, and what I'm going to get it, this is 2.016490 atomic mass unit. So this is what, when I add the mass of the hydrogen and the mass of the neutron, this is the mass expected to get the mass of the deuterium atom. But what experimentally we know that the experimental, or I can say the actual mass of the deuterium is 2.014102 unit. So if I compare these two mass, so naturally I'm seeing that the mass of this is less than the mass of the deuterium, which I get by adding the mass of the hydrogen atom and plus the mass of the neutron. Okay, so this delta m, the mass of, if I say delta m, this is mass of, uh, okay, this is basically less than. So this delta m is mass of, okay, deuterium. This is which this mass of the hydrogen plus mass of this minus mass of the deuterium, which I get experimentally. So this is around 0.002388 atomic mass unit. So this delta m, the mass difference between the expected mass 0.002388 U. So the major mass of the deuterium atom is this one, which is experimentally measured, and we found that this is actually this much less than the mass which we get by combining the mass of the hydrogen atom and the mass of the neutron. So what comes to mind is that the missing mass, the missing mass is this one. This is my missing mass. This much mass is missing mass. While when we add these hydrogen and neutron and then we combine this to make the deuterium nucleus, deuterium atom, this much of mass is not there. So this is a missing mass. So where this mass is? So what comes to the mind is that the missing mass might correspond to the energy given off when the deuterium nucleus is formed from a free proton and the neutron. So what comes to the mind is that this missing mass, uh, this missing mass, this missing mass must correspond to what? Correspond to the energy given off uh, when a deuterium atom or deuterium nucleus or atom is formed from a free proton and neutron. So what I have to do is I have to calculate the energy equivalent of this missing mass. So what is the energy equivalent? What is the energy equivalent of this missing mass delta M? Now let us calculate it. This is very easy. We know that how to calculate this. Delta E will be delta M. Okay, we have already calculated uh, times C square, and we know that one atomic mass unit is around uh, 931.49 MeV. So delta E will be delta M times, we will multiply it by, because this is in unit of this, then 931.49 MeV by U. So this is like 0.002388 U, and then it will be multiplied by 931.49 MeV by U. So this comes out to be 2.224 MeV. So this much of the energy is being given off when we combine a nucleus, combine a proton, a free proton and free neutron to form a deuterium nucleus. Okay, so to test this interpretation of the missing mass, that really the missing mass energy equivalent uh, of this missing mass is given off when we try to synthesize this deuterium nucleus out of this free proton and the free neutron. So how to test it? So we can perform an experiment to see how much energy is needed to break apart a deuterium nucleus into a separate neutron and proton. So what we try to do is, if I have a deuterium nucleus, so if I have a nucleus in which I have say I have a neutron proton and I have a neutron is there. This is my deuterium nucleus. Okay, so this is my deuterium nucleus. This is my deuterium nucleus. So how much energy I must supply? If I supply an energy through a photon, uh, this energy, this is known as the gamma ray or photon. Okay, so if I supply this much of energy in order to break this deuterium nucleus, how much energy I need in order to break this deuterium nucleus into what? Into a proton, separate free proton, and a free neutron. This is proton and this is neutron. So what experimentally is found that the required energy indeed turns out to be 2.224 MeV. So this is energy is needed to be 2.224 MeV. So if experimentally if I want to break this deuterium nucleus, then if I have to supply this much of energy, 2.224 MeV of energy, so that this proton and this neutron, which is combined in the deuterium nucleus, it become free as a free proton, as a free neutron. When less energy, when we have supply less energy, then if you supply less energy, then if you supply less energy, if say this is energy of this photon, if I supply gamma of this is less than 2.224 MeV is given to the nucleus stays together, doesn't break up. Okay, and when we add energy which is more than or say when we supply energy is which is greater than or equal to 2.224 MeV, then what happens then? This much amount of energy is used to break the deuterium nucleus into a free proton and a free neutron, and the extra energy, if it is more than 2.24 MeV, is distributed to have the kinetic energy of this free proton and free neutron. So as they fly apart, when they are they are being free from the nucleus by using this energy of 2.224 MeV. So yes, that when we add a free proton and a free neutron to make a deuterium nucleus, then what we found that there is a missing mass. The actual mass is actually less than the mass when we add the mass of the proton and the mass of the neutron. And the energy equivalent, which is 2.24 MeV of this energy equivalent of this missing mass, is given off when we create this nucleus. And this has been experimentally verified that yes, we need this much amount of energy, 2.224 amount of energy, if we want to break this nucleus apart, if we want to break the constituent of this nucleus, proton and the neutron, to be free out of this nucleus. So this established as the missing mass is basically the energy equivalent. So deuterium atoms are not the only ones that have less mass than the combined mass of the particles they are composed of, but all atoms are like that. So all atoms are like that. Any atom which you combine through their constituents, and if you add the mass of the constituents, and that will be more than the mass of the actual system uh, out of which made up of these constituents. So the energy equivalent of the missing mass of a nucleus is called the binding energy of the nucleus. So now finally we can say that very safely that the energy equivalent of the missing mass of the missing mass of a nucleus is called the binding energy of the nucleus. Okay. So the greater its binding energy, the more the energy that must be supplied to break up the nucleus. So if we have the more binding energy of a nucleus is more, then I need more energy to break that particular nucleus into its particular constituents. So how to mathematically we write the binding energy? So binding energy can be written mathematically as that EB, it's a binding B is for stand for the binding energy is equal to, so say, Z times the mass of the hydrogen atom. Because why I multiplied Z? Because Z will give us the number of proton. This is basically the proton and the mass of the proton with the electron are equal to. So Z will give us the number of proton and electron, and then N will give us the number of neutron, and then that is multiplied by the mass of neutron. Okay, and then this minus mass of this will be the atomic mass, not the nuclear mass. So mass of the system, AXZ, AXZ. And then because we're talking about the energy equivalent, so I have to multiply it by 931.49 MeV per U, because all these are in unit of atomic mass unit. Okay, so I can write it where M is atomic mass of hydrogen atom. When I say atomic mass, that means the mass of the electron is also included. Okay, and Mn is the mass of the neutron, is neutron mass, and Mx AZx is the atomic mass of Z, and all these are in unit of the atomic mass unit. So as mentioned before, the atomic mass, we are using the atomic mass, not the nuclear mass. That means I'm using the mass of the electron also here. Okay, so not the electron mass subtracted. So this is how we calculate the binding energy of any system. Let us take one simple example to understand this use of this binding energy formula, that uh, I have been given the binding energy of neon isotopes. If I have a neon isotopes in which we have, this is 10 proton, this we have 10 protons, and then we have 10 neutrons, because this is my A and this is my Z. So N will be A minus Z. Okay, so this is 10 proton and 10 neutron. So the binding energy EB of this is given as 160.647 MeV. So what I have to do, I have to find the atomic mass, the atomic mass, the atomic mass of 20 neon 10. So now I can use this formula very safely. So from here this is my atomic mass. Okay, so this is basically if I write this formula as EB, which is given in MeV, so this will be basically in MeV, so equal to uh, Z I have is number of Z, so Z is 10, 10, and this so let me first write it. Let me first write the formula. This is Z times mass of the hydrogen atom plus n times the mass of the neutron minus m times. This is my 20 neon, 20 neon 10. Okay, and then I have 931.49 MeV per U. So I have to calculate this quantity. So this I can write it as mass of this 20 neon 10 has to be, because uh, Z times the mass of hydrogen atom plus n times uh, mass of the neutron, and then minus EB divided by 931.49 MeV per U. So this I can calculate it, because number of Z is 10 here, so I write 10 and then multiplied by the mass of hydrogen. This will be provided. This is 1.007825 in atomic mass unit, and mass of the neutron is also 10, so this 10 times the mass of neutron is 1.008665, which is in terms of atomic mass unit. And then we have EB is given, EB is already given, this is 160.647 MeV, and then I have 931.49 MeV per U, and this comes out to be 19.992 U. So this is what we have, the atomic mass. So then if you have been asked to calculate the binding energy of this system, this neon system, then you have been provided what is the mass of the hydrogen, mass of the neutron, and as well as the mass of this 20 neon 10. All these will be provided to you. So what you just have to put all these values here and then multiplied by this, you will be getting the mass of the binding energy of neon atom. Okay, so this is a very brief discussion of the nuclear binding energy. So but the nuclear binding energy are strikingly high, because the range for a stable nuclei is of the binding energy is around EB is binding energy rise from, like, this is 2.224 MeV, as I have started with the deuterium, the lightest nuclei, which was of deuterium nuclei, to like this goes to 164 times MeV in case of bismuth nuclei, which is like having 209. If two nucleon is there, so if I have to break apart a system which has two nucleon, then I need this much of energy. If I have a nucleon which is system which is consisting of 209 nucleons, in which consist of 83 protons, we need 1640 MeV of energy, so much of energy. So to appreciate how high energy nuclear binding energy, we can compare them with more familiar energy in terms of the kilojoules or energy per kilogram the mass. Uh, you know that when you boiling a water, how much boiling a water, how much it contains energy? Do you know that? So boiling water involves uh, heat of vaporization of around say I can say 2260 kilojoule per kilogram. And then if I burn a gasoline, uh, and then gasoline burning, if I compare, that will give you heat of like 4.7 into the power 10 to the power 4 kilojoule per kilogram. But if you compare the binding energy in terms of the kilojoule per kilogram equivalent, then you can see that uh, a typical binding energy, a typical binding energy value correspond to 8 into 10 to the power 11 kilojoule per kilogram. Okay, so now you can compare it. A typical binding energy, I'm not saying this much of energy, a very typical in between, is corresponding to 8 into 10 to the power 8, and you can compare boiling water involves only 2260 kilojoule, and this is 10 to the power 8. Gasoline burning is 10 to the power 4, and this is 10 to the power 11. This is 17 million times smaller, 17 million times smaller than this value. So now you can imagine that a typical binding energy gives so much of energy in as compared to our daily life energy, which we concern of. So the nuclear binding energy, therefore, a very uh, high, striking high energy that is used into the fusion or fission process. So this is all about the binding energy. And the next one is I would like to discuss is about the binding energy per nucleon. So let me say that this is binding energy per nucleon. So what is the binding energy per nucleon? So as the name suggests, the binding energy per nucleon for a given nucleus uh, for a given nucleus is an average found by dividing its total energy or its total binding energy by the number of nucleons. Nucleons means proton plus neutrons it contains. Okay, so so thus as we know that the binding energy, so binding energy of deuterium is how much? Is 2.224 MeV. So the binding energy per nucleon, so binding energy per nucleon, or we can say that this is binding energy divided by A of this shown. So this will be 2.224 divided by 2. This will be 1.11 2 MeV per nucleon. Similarly, the binding energy per nucleon for say 209 bismuth 83 is, because the binding energy of bismuth we know that 1640 MeV, and this has to divided by this is how much amount the 209 number of nucleon is there, so this will be 7.8 MeV per nucleon. So let me draw, if we calculate the binding energy per nucleon of all the nuclei which we have. So if I draw this if we draw a graph, say this is like this. If I plot the binding energy of all the system, binding energy per nucleon, if on the x-axis I have mass number A, and the y-axis binding energy per nucleon. So say this is my binding energy, this is per nucleon in MeV. So what I will get is like, this will be, so 4, so let me draw it. This will be like, so here I have like some, this is say 56 iron, which is 26, and here this is 4 helium 2 nucleus. So this is what I have is the mass number on the x-axis and the binding energy calculated for all the nuclei, and if I plot it we get a curve like this. So what conclusion we can draw from this curve is that uh, so the greater the binding energy per nucleon, the more stable is the nuclear is. So first conclusion we can have uh, the greater the binding energy per nucleon, the more stable the nucleus. So you can see the graph has its maximum of around if I say that this, if you point out this point, so this correspond to around 8.8 MeV. This correspond to 8.8 MeV. So the graph has its maximum of 8.8 MeV per nucleon. When the total this point correspond to this iron nuclei. So the maximum number of nucleon is 56. So this nucleus has 56 uh, 26 protons and then 30 neutrons, which is an iron isotope. So this is the most stable nucleus of all of them. So all the nucleus or the atomic nuclei we have in our periodic table, so 56 iron 26 is the most stable. Iron isotope, because it is having a maximum binding energy for nucleon. So this is the most stable nucleus of all them, since the most energy is needed to pull a nucleon away from it. So why it is most stable? Because this is most stable because I need an 8.8 MeV per nucleon energy to remove a neutron or proton from this iron isotope. So other two remarkable conclusion can be drawn from the curve is that the first one is try to understand it. The first one is that if we can somehow split a heavy nucleus into two medium-sized one. So if I have a heavy nucleus, say I have a heavy nucleus, and if I split this into two small, then what I'm going to have plus energy. This is energy. So if I have, let me draw it first. So if I can somehow split this heavy nucleus, split this heavy nucleus into two medium-sized ones, this one and this one. Each of the new nuclei will have this nuclei or this nuclei is going to have more binding energy per nucleon than this nuclei. So if I say this is A and this is B and this is X, so what I am saying that EX, EA as well as EB, or let me say like this, the binding energy per nucleon of EA or the binding energy per nucleon of EB will be more than the binding energy per nucleon of the original nuclei. This extra energy will be given off, and it can be a lot of energy. Why it is so? Because you can see that from the graph, you can see that here the mass number is increasing. So that means if this is a bigger nuclei, if this is my bigger system, so it is going to have more A number, and this is a smaller, so it is going to have less A number. So that means if I break this heavy nucleus, so I am somewhere here, okay, and then if it's break into a smaller nucleus which are going to have a smaller A number, so then I am moving towards this. So when I am moving towards this, the graph is increasing, the slope of graph is increasing, okay. So that means the energy per nucleon is increasing, and that energy is very much. So for example, if we break the uranium nucleus at 230, like 235 uranium 92 nucleus into two smaller nuclei, the binding energy uh, difference per nucleon is about 0.8 MeV. Okay, so if I break this nucleus into two smaller system, so the binding energy difference per nucleon is about 0.8 MeV. So if I calculate the energy equivalent of 0.8 MeV uh, MeV per nucleon, if we calculate it, and this we have 235 number of nucleons is there. So you can see that how much of energy, this is 188 MeV. So this is a lot of energy. So similarly, uh, So because this is a truly enormous amount of energy to be produced in a single atomic event. This is a single atomic event. So if it's so much of atomic event is there, so you can imagine how much of energy has to be there. So uh, as we know that ordinary chemical reactions involve rearrangement of electrons in atoms and liberate only a few electron volts of energy. Electron goes from this energy cell to this S to P, and then in this rearrangement we have only a few electron volts per of energy is per reaction is there. But is splitting a heavy nucleus, which is this kind of reaction, is known as the fission reaction. This is known as the nuclear fission. This is known as the nuclear fission, and this involves 100 million times more energy per atom. And say that the burning of a coal or oil, 100 million times energy. So you can see that if I break a bigger nucleus into a smaller nucleus, the binding energy per nucleon increases because we are going towards this side. The slope is increasing, and this process is known as the nuclear fusion. And then we have, in that process also, we have given off more and more lots of energy. The other notable conclusion is that the joining of two light nuclei, if I join these two light nuclei here, if I have one light nuclei and then another light nuclei, if I join these two light nuclei to get a bigger one, so I have one nuclei is there, one nuclei is there, I get a bigger one. Okay, so this is my X, this is my A, and this is my B. If this process is there, what will happen? So if we have two light nuclei together to give a single nucleus of medium size, also means more binding energy per nucleon in the new nucleus, because this here also this now this Ex binding energy per nucleon is greater than either AB per nucleon or EV per nucleon, because in this case I'm the lighter nuclei are on this side, and when the mass is increasing I'm going on this side. So and here also we are going like in this direction, so the binding energy per nucleon is also increasing here. So in this case also we are getting more and more energy. So if we combine uh, two deuterium nuclei, for example, if I have two deuterium nuclei, if I have 2H1 plus 2H1, so this will give us 4H2, 4 helium 2. So this is a helium peak, which is extraordinary peak. All of a sudden you get a rise in the binding energy per nucleon, then it decreases and then goes on increasing. See, for this, I know this is 2.224 MeV per nucleon, so energy uh, per nucleon, this is 1.112, and this is also 1 point, I have calculated it, this is 1.11, this is also 1.11, and then this goes up to like uh, completely around 7.5 MeV. So we have seen that that this bigger nuclei Ex, uh, this bigger nuclei Ex binding energy per nucleon is this is greater than the binding energy of individual per nucleon of the constituents. These lighter system, these two lighter system, this one, or say uh, mm, this one, if we add this to this system, and then what we have is like the bigger one, the bigger system. So binding energy per nucleon increases. So we have seen the example that this 2 deuterium plus 2 deuterium give us 4 helium-2, and the binding energy per nucleon is 1.1 MeV. This is 1.1 MeV, and this around 7.5 MeV. So this is a huge difference. Okay, so much lot of energy will be given off when two medium light nuclei is combined to give a medium sized nuclei. So in this process also, which is known as, this process is known as the nuclear fusion. This process is known as nuclear fusion. So in this process also, the energy, lot of energy is given off. So these are the two important points which comes out of the binding energy per nucleon. In fact, the 4 point in which we have, the first one is, the more the binding energy per nucleon, more stable is the system, and the iron 56 iron isotopes is the most stable one among all the nucleus. And then if we break a bigger system to the smaller system, then also we have lot of energy given off in that process, which is known as the nuclear fission process. And then if we add some smaller nuclei to give a medium-sized nuclei, then also the binding energy per nucleon increases, and that ultimately give rise to a lots of energy given off in that process, which is known as the fusion process. In fact, the fusion process is the basic process in all the stars, and what we use the stars energy is through the fusion process. In sun, the fusion process is going on, because of which lots of energy is coming out, which we get in terms of heat energy. Now let us consider one example which will clear more this will about this binding energy process. So the example is like uh, tells us find the energy, tells us find the energy needed to remove a neutron from the nucleus of calcium isotopes, which is 42 calcium 20. Okay, and then also say a neutron, and as well as I can add and proton. So we have to find the energy needed to remove a neutron as well as a proton from this calcium isotope 42 calcium 20. So let us try to calculate it. So you know that if we have a 42 calcium 20, if I remove an electron, if I remove a neutron from this system, this becomes 41 calcium 20, because here we have number of proton is 20 and the number of neutron is 42 minus 20 is 22. So this is number of neutron. If we remove one neutron, and this becomes 21, so 21 and 20 becomes 41. Okay, so this becomes 40 calcium. So what happens that we can think of that if we do a process in which 41 calcium 20, if I add neutron one neutron to this system, this is my neutron to this system, then I'll get this system. Okay, so this plus this will give me this. So if I add the mass of neutron and the mass of this, then it has to be mass of this, then the missing mass we can get it. Okay, so if I add the mass of this 41 calcium 20 and the plus mass of the neutron. So then what I'm going to get is this is 40.962278. These masses, if you have been given these type of numericals, then the masses, atomic masses will be provided to you. And the mass of the neutron, we know this is 1.008665 U, and this is equal to 41.970943 atomic mass unit. So the difference between this mass and the mass of 42. So uh, so this delta M is naturally this mass has to be more than the mass of this. So the mass of 41 calcium 20 plus a neutron minus mass of 42 calcium 20, if you calculate it, this will come out to be 0.012321 U, and the energy equivalent, if we calculate for this mass, is 0.012321 U, then multiplied by 931.49 MeV per U. This comes out to be 11.48 MeV. So this much of energy needed to remove a neutron from this 42 calcium isotope. But what about proton? So if I talk about the proton, so let me calculate it for proton. So if I have 22 calcium 20, so we have 20 proton and 22 neutron. So if I get a proton out of this system, so the proton becomes 19, and then total this becomes 41, because then 19 plus this becomes 19, and this is 22, this becomes 41. This becomes 41 K19 system. So if you calculate this mass of, if you add this plus, then if you do similarly, if you add this and plus a proton to the system, then I'll get this system. Then to the mass of this system calcium, then mass of the proton, and this mass of this calcium. If you take the difference delta M, if you calculate the delta M, and then the corresponding delta E, if you calculate, this comes out to be 10.27 MeV. So the important thing to notice is that when I need to get a neutron, remove a neutron from the same system, it is 11.48. When I need to remove a proton from the same system, I get a lesser energy. Why it is so? That E proton is less than E neutron for 42 calcium 20. So this is because when we deal with the proton, so proton is a charged particle. So if my inside my system, if the neutrons are there, and I have a proton is there, in the system, if this is my system, then what happens? The neutrons are only affected by nuclear force, nuclear attractive force. But what about proton? But protons being charged, they also repelled via Coulomb repulsion. So this repulsion force which is acting between the two protons is also helping out to get a proton out of the system. That is why we need a lesser energy as compared